let's focus in here. Okay. So, this week, quiz on cycloalkanes. So, chapter 4. Nomenclature, drawing cycloalkanes by name, cis and trans isomers. So make sure you can draw cis and trans isomers. And drawing chair structures, okay? And drawing the most stable or least stable chair conformer and circling it. So be able to draw both chair forms, okay? One way to draw it, and then you chair flip. Remember, in the chair flip, the only thing that changes is not the stereochemistry, but the axial and equatorial locations of the substituents. Okay? So that's your best bet to review there. So review those topics for the quiz. Okay? And then the last week's quiz, I'll pass them back during lab on Thursday. Okay? Before we start doing the experiment. Are there any questions about what to prepare for lab on Thursday? It's not a workshop this time. It's an actual experiment. Are there any questions about that? So make sure the procedure is not that long. So your time for your pre-lab there, just summarize what you'll be doing in the procedures. So you know what you're doing during lab, right? And that's kind of proof to me that you read before the lab takes place, okay? And also include the safety info for the main chemical we'll be working with, all right? Acetaldehyde, name of the chemical, molar mass, hazard pictograms, what kind of safety hazards should you expect? And if you do get exposed, what is the first aid info, okay? So on the first day module, I did post, some stuff for writing pre-labs. So you can look at that. There's like that safety data template. You can print that out and then just paste that in for each chemical you have to work with. I think it's only one though. Water doesn't really count, so I won't expect you to write anything for water. Okay, but for anything organic, we will have to be aware of the safety concerns. Okay, Catherine, what's up?
For the table of contents, do you want this experiment to be like going with the first page?
No, that's all right. So you already have a notebook. You can just be like, okay, first page, workshop 1, blah blah blah. So wherever it is in your notebook, just put that page number. Yeah. Okay, and then please have a notebook, or if you like, have a folder with binder paper in it. That's perfectly fine too, like in Chem 1A and 1B. I think that's pretty much it. If you have any specific questions, feel free to ask me. Okay, and then the list of chemicals, they're in the procedure. They may not necessarily be at the beginning of the experiment, so just be aware. As you read the procedures, just be on the lookout for the chemicals you'll be using, okay? All right. Are any other general questions? Nope. Well, homework this Thursday. Chapter 4 homework is due, and then I'm making chapter 5 homework being due the following week, because the week after next week is the second exam, okay? So we need to get chapter 5. Chapter 5 is a big chapter, okay? And make sure we understand that material, okay? So chapter 5 homework is then due on the 2nd of October. All right. And there's no general questions. Let's just hop right back in here. All right. So we talked about enantiomers. Enantiomers, you can actually, you can tell if you have an enantiomer because it interacts with light, okay? So one thing we could actually record is something called optical activity. So optical is just another word for light. Optometrists, they help you treat your eyes or check your eyesight, because your eyes are the primary way we interact with light in the world, okay? So, optical activity. So, ordinary light it has a mixture. Like white light is a mixture of all colored light, so that has a light of many different wavelengths. Okay, so it's made up of many EM. So the EM stands for electromagnetic, okay, radiation or waves. So many EM waves here that move in different planes. So by planes, I mean like many, I guess you could call it dimensions, but planes like flat surfaces in many directions, okay? Many move in many different planes. So description here, a physical description. We could draw a light bulb. Okay, so say this is my wire. Here's my light bulb, and it's going to give off many different waves here. Okay, so how we can tell if something interacts with light is if you have a polarizing filter. So I'm going to draw a filter here. All right, so this would be my polarizing filter. Okay, and out comes light moving in a specific plane. Okay, so here I could write something like right here. So say this is my direction here. And the light here will be plane polarized, so it's only occurring in one plane, okay? So here's my wavelength, okay? So this will be my plane polarized light. Plane polarized light. Okay, so remember, these waves, they can come in many directions. We polarize it to one specific plane, okay? We then run it through our chiral sample. Okay, so your molecule, your enantiomer here, has a chiral sample. Okay, so this typically, this sample cell is typically 10 centimeter path length. Okay, so very short. It's like a, if you guys ever worked in the lab, it's like these tiny cuvettes that you put in like a spectrometer and you shine light through it, and you record the absorbance, okay? So what comes out here is something very similar, but now the waves are going to be rotated a certain degree here. So I kind of wrote this slanted to indicate that the waves have been rotated in one axis, like rotate a certain degree, okay? So that's what that means. So here we can have rotated plane polarized light. All right, I might want to move that over a bit. All right. Okay, and then lastly here, what happens is you're going to have a filter. Okay, so this will be my rotating. So we call it a slit or an opening slash polarizing filter. Okay. And then so the light then will be rotated, okay? And then at the very end here, okay, this last part, this is the detector slash observer. Okay, so that's when we get a readout. We're like, okay, we put the light through our sample, it rotates that light, it goes through this polarizing filter, and then it reaches this detector that we can now determine how much the light has been rotated by our sample. And that's the number we see, and the number is usually in degrees, okay? So that's how we tell if like, what stereoisomer do we have? Well, there's usually a standard that you would have. And then you would calculate, you would run it through this instrument called parameter, and it will tell you by how much it has rotated. Okay, and then that will give you a value. Now, if you have the other isomer, the other enantiomer, your value would be the same, but it will just be opposite in sign. So that's how you tell which enantiomer you have. Number, is it positive or is it negative? Okay. All right, so that's kind of how light is rotated, and that's how we tell if something's chiral. Okay. So the thing about chiral molecules is that they would have, so chiral molecules are said to have optical activity. Okay, that means you can record this angle of rotation here. We call them optical activity, or they're optically active molecules. So if something is optically active, it must be chiral. Okay, and then you can have a mixture of this optically active characteristic, but usually if something's chiral, you would record optical activity. Okay. Then on the contrary, achiral molecules, they can't interact with light. Okay, because one half of the molecule is the same as the other half of the molecule. They're symmetric, so they'll just interact with it. They won't interact with it any differently from another isomer, right? So that's why they don't interact with light at all. Okay, there's no preference based on if it's the right-handed isomer or the or the left-handed isomer. There's no preference. Okay, so they do not rotate light. Okay, so in this case, their optical activity is 0. So they don't rotate the light at all. Okay. All right. So the common ways we measure this value here. So we measure rotation of plane polarized light as an angle of rotation. Okay, so it's usually some number in degrees, and we use a special instrument called a polarimeter. All right, and it's this big instrument, and you have a cell where your sample goes. So it looks very similar to this box diagram I drew up there. Okay, one side is the light. Okay, and I'll talk about like how do we measure it, like what light exactly do we use. Okay, all right, are there any questions about how molecules can interact with plane polarized light? So if something's symmetrical, they can't interact with it, so that's why you don't see any value for achiral substances. All right, so optical activity, that's just measure how much a molecule, a chiral molecule, can rotate light a certain number of degrees. Okay, so something's chiral, it'll have octave activity, and octave activity basically, it depends on a few things. How chiral is the molecule? Is there more than one chiral center? And stuff like that. So you can't really predict the value. Those things are experimental by just by how they're made. Okay, or how the molecules are constructed and the shape and all that. All right, so you don't have to memorize any values. Any values will be provided to you, okay? But now let's talk about some of the math you might encounter here. It's not that bad. Simple math, okay? So let's talk about specific rotation. Just like there's specific heat, there's specific rotation, okay? So it's defined defined in such a way that the specific rotation is always just a constant, okay? All right, so in brackets here, this is your alpha, that's your angle, specific rotation, and it's usually taken as some temperature in degrees, and then the letter D here, okay? D refers to like the rotation. What light source did you compare it with? If you use different light sources, your specific rotations will all be different for the same compound. So that's why we use it's defined specifically so comparisons can be made across different compounds, okay? So when it's not in brackets, this is a different value of alpha. And on the bottom, L times C, okay? So let's go over each of these terms. So the one on the left, so we have our alpha in brackets at a certain temperature, and I'll explain what the letter D means, okay? So this is our specific rotation. Okay, so this is a physical constant, a physical for a compound. So it does not change. It won't change at all. Okay. All right. So the letter in this notation, the letter D stands for the wavelength. So wavelength of sodium, a sodium lamp. Okay. So in this case, it refers to the sodium D lines, so each of the lines in the emission spectrum. Remember, maybe in Gen Chem, you looked at gas discharge tubes and you saw the electronic structure or the colored lines for each atom. So the sodium lamp here, this refers to the line, the sodium D line, and that's the line at 589 nanometers. So that one looks like kind of red-orange, the orange line of sodium, okay? All right, now alpha is very, it's similar, but that's the observed optical rotation. So this is the value that changes based on concentration, okay? So this is in degrees. All right, so what's important here is to use this equation, and we'll show some examples in a bit, okay? So L here, that's your path length. So when light hits your sample, right, depending on the dimensions of the sample cell, it will have light will have to travel a certain distance to go through your sample. And then based on how much light was absorbed, you can measure a lot of things. In Gen Chem, you probably use absorbance. You measure the absorbance versus concentration. Here, we're going to measure optical rotation, okay? So L here is the path length. So path length of sample container. All right, and this is in a special unit. It has to be in decimeters. All right, so the typical value here is 1 decimeter. Value is 1 decimeter, okay? All right, then 2 more things here. C, what is C? That stands for not the speed of light, that's the concentration. In grams per mil. All right, so not moles per liter, grams per mil. And the T here, the last one, T degree equals your temperature in degrees Celsius, like that. Okay, so degrees Celsius will be our temperature. All right, are there any questions about these symbols here? So they're all part of specific rotation, okay? Captain, what's up?
So concentration of what?
Oh, your concentration, it'd pretty much be your compound. So like of substance or your compound. Yeah. Yeah, so anything achiral, like you put water in there, methanol, nothing will happen because it has no stereocenters. Okay? All right. All right, so that's specific rotation. All right, so let's talk about enantiomers. What happens when you put them in a polarimeter? So, enantiomers are mirror images. Okay? So what you should refer to this as, it rotates plane polarized light. All right. So, if they're enantiomers, right, we expect them to rotate light, if they're mirror images, right, the same amount, but what's the difference? Will they rotate it in the same direction? No. Opposite direction. Your mirror image is like the opposite view, right? It looks the same, but it's reflecting your opposite image. So equal amounts, but opposite directions, okay? By equal amounts, okay, but in opposite directions. Okay, so one rotates something 30 degrees. The enantiomer should rotate it oppositely, negative 30 degrees. Okay? All right. So one thing we could do here is that we could use polarimetry, so the degree of rotation is a way, sorry, that's an A, to measure percent purity, okay? So what do you think what happens if you have a mixture of enantiomers? Well, if one rotates one a certain direction and another rotates the other direction, what do you think is going to happen? They'll cancel each other out, okay? So you can actually here use percent purity, use degree of rotation. So that's pretty useful. Because one, you just measure it in an instrument. You're not destroying the sample. It doesn't take much sample size. So you can actually, it's a very useful way to, characterize purity, especially if you have drugs that are chiral. Most drugs are chiral, okay? Like some of the bigger ones. Simple ones like acetaminophen and stuff like that, Tylenol and all that. Not stereoisomers, but when you get to more complicated drug molecules, they have many chiral centers, so that degree of purity will be important. Okay? All right. So what percent purity I mean, though, is I'm referring to optical purity. Okay, so we can also separate enantiomers using chiral separation methods. So that's one way you can see I have the plus or minus isomer on sigma. I could purchase it. All right, so there's ways to separate them. All right, so but how do we measure purity? There is an equation, so let's write it down. So percent optical purity equals, all right, in parentheses, let's write our alpha observed our alpha for a standard value. So this will be like your pure chemical, your pure substance, the pure enantiomer, all right, times 100. All right. So based on what this number is, you can actually find out how much percent excess you have for a set of enantiomers. So here, percent, we also often call this percent EE or percent enantiomer excess. So another way we write this is percent EE, okay? Because enantiometric excess, that's too many E's, so we just reduce it down to just percent EE, okay? All right, so there's two terms for mixtures of enantiomers that we should know. One of them is called racemic. All right, so let's write this, racemic mixture. All right. Contrary to how the word sounds, has nothing to do with race, okay? Racemic mixture refers to enantiomers, all right? So, it's a mixture that contains, okay, equal amounts. So, if we're talking about 100, right? Equal amounts would be, what, 50-50, right? 50-50 mixture. So, we have a 50-50 mixture, okay, 50-50 mixture of two chiral enantiomers. Okay. So, if they're equal amounts, would your mixture be chiral though? What do you guys think? All right, let me ask it a different way. Would this mixture be optically active? No, right. So here we can say such mixtures are optically inactive. So it's like if you you don't have any of the stereoisomer that you want, so you even though it says 50-50 a plus and minus enantiomer, that optical activity will be 0 because they both cancel each other out. So there's no really net rotation of light here. And so your stereoisomer will be considered inactive, all right? So usually you don't want a racemic mixture, especially if you're trying to make a specific isomer of a drug, okay? All right, there's another term that we'll go over here. So if it's not 50-50, it's called scalemic. So a scalemic mixture. All right, mixture of enantiomers that are not equal, okay? So this would be not 50-50, so not 50-50, okay? These mixtures, do you think they'll show activity or no activity? Yeah, they'll be optically active because you have an excess of one enantiomer, so you're going to show some rotation here. All right, so we know that enantiomers are optically active, so they'll rotate light either positive direction or the negative direction, okay? So let's do an example here. So I'm going to draw two molecules here. So this is an optically active molecule. All right, and here's my mirror plane to indicate this is the other enantiomer. So CH3, and my carbon right there, CH2, CH3, BRH. All right, so the specific rotation of each of these at 25 degrees Celsius, the sodium D line, the enantiomer A, negative 23.1 degrees is for enantiomer A. All right. And then enantiomer B What do you think an enantiomer B would be? Okay. So this is the enantiomer B. What value should this one have? Yep, thank you. All right. Okay, so now let's make a little chart here. So I'm going to write an ant A, an ant B, and now here I'm going to write observed rotation. You got a question?
Is that 2.5 or 25
Where?
for the temperature for?
Oh, yeah, 25. Yeah, this is 25. Yeah. So these are always at room temperature. Yeah. Okay, so say we have 50% of A, pure A, 50% of pure B mixed together, 50%. All right. It should go. All right, we might be lagging here a bit, guys. All right. What should be the observed rotation if you have equal amounts? 0. Good. Now, what if you have 25% of A and then 75% of B? What would you expect? All right. $75. Oh, my phone. Sorry, guys. All right. What do you guys expect here for 75% and 25% of A? All right. Well, we know that 75% of B, well, how much of it will combine with A? Right? So we have 25% of A, right? So 25% of B will be canceled out by A. So what's my excess then? 50. So I'm going to take 50% and times it by the rotation of B. So what's the value for B? Oh, no, sorry. The value for the rotation of B. Yeah, so it's 23.1, right? So that's going to be about 11.55 degrees. Or you can just say 11.6 since it's 3 sig figs. All right, now let's see how we got that number. We took the excess amount, so this is my excess of B. Okay, so you're going to take the excess amount of B, take that fraction, multiply it by the specific rotation, which is 23.1 degrees, and you get the observed rotation. Okay, so this one would be 0 times 23.1 degrees, and this would give me 11.6 degrees. All right. Okay. Are there any questions about that example? So we're taking the excess and doing like so. All right. Now let's do this one. How about 60 of A and 40% of B? How much excess do I have in this case? 20% of which one? A. So we're going to use 0.2, that's 20%, right? Times negative 23.1 degrees. Okay.
Can you remind me, the negative 23.1 degrees, what are you calling that term?
So that's our specific rotation. Yeah. So observed rotation is always, it takes into account the excess you have and then the specific rotation of that specific enantiomer. Right. All right, what do we get here? Negative. Well, don't worry, you don't have a calculator, it's fine. Negative 4.60 degrees. All right, so see here, equal amounts, no rotation, and you have slight excess of each is going to be a fraction of the actual rotation here. And then sometimes, mixtures are okay. As long as there's some optical activity, it might work as expected. But for purity here, you want to be close to 100% to get the right enantiomer. Okay. Are any questions on that math? So find the difference. Find the percent EE. So this is percent EE here. Okay. So this is another term for percent EE. Okay. And then you're going to times that by the observed rotation, sorry, not the observed, specific rotation of your enantiomer, and then that resulting number is your observed rotation that you would see if you put it in an instrument. Okay? All things else working perfectly, of course. Like the instrument has been checked, verified, checked for accuracy. Okay? So there's a lot of things in science. There's a lot of things you have to consider to be objective here. All right. So let's do an exercise relating to this example. So let's do exercise A. Okay. All right. So say we have the same compound. So this compound right here is 2-bromobutane. Okay. So say you have a sample of 2-bromobutane, and its observed rotation is positive 2.31 degrees. Okay. I'm just saying out loud right now because writing it is very slow for some reason. Okay. So we have a sample of 2-bromobutane has an observed rotation of plus 2.31 degrees. All right, my question for you is, what is the composition of an enantiomer? So what percent is A and what percent is B? Okay, so what is the composition of the sample? What is the composition of the sample? All right. All right. So if it's positive 2.1, so we can actually do it this way. So we have positive 2.31, right? Let's take positive 2.31. And then, so if it's positive 2.31, we have an excess of which enantiomer, you think? A or B? B. So what's the value for the specific rotation for B? 23.1. All right. Now, we times this by 100, we'll figure out what ratio or what percent excess we have, okay? So if we do this and times this by 100, what percent is that? 10%. So we have 10% of B. All right. That must mean how much of A do we have? No, wait, let's think about that. We have, be careful. So you might think, oh, it's 9% A, but what's the problem with that? You'll have 80% excess, right? So that can't be right. So this means excess. So is there a way to have 10% excess? Let's see. What would, so we can't do 60-40, right? That's 20%. So what if we subtracted each of these numbers by, or subtract this by 5 and add this by 5, what would we get? 55, 45, let's not put it right there. So wouldn't that add up to 100? Yeah, so this will give us 100. So, our excess here is 55 and 45. Okay, so you gotta be careful. Just think, okay, 60-40 looks like a good cutoff. We can't do 50-40 because that only adds up to 90%. So you have to add 5 to one, subtract 5 from one and add 5 to another to give you a 10% excess difference. So here we're going to have 55. So let's write here 2.31 over 23. Well, I wrote on the board equals 10%. Okay. Well, to have an equal value here, we have to have 55%. Is that going to be A or B? B. And 45% of A. Okay, so what this means is excess. So you won't want to say 10% B because that just means 10% excess. So you have to come up with a number ratio where the difference is 10 and it still adds up to 100. Okay? All right. Are there any other questions on that example? No? All right. So let's take a 10-minute break and we'll resume by talking about RNS configurations. Okay, the stuff we were kind of talking about in lab the other day. Yeah.
What did you say the quiz was gonna be on?
Chapter 4.
But like
Chair cyclohexane, drawing chair structures, nomenclature, and drawing the cycloalkanes in general, cis and trans.
okay,
Yeah.
thank you.
Oh, yes, up.
I have a question, but I just wanted to let you know for first I won't be here.
Oh, okay.
I have a really big anatomy exam.
Oh, yeah. Now he's hard. Okay,
Yeah,
stay
it's on
up.
all the bones, muscles, joints.
Oh, wow. That's a big,
So yeah,
big part of the human body.
yeah, so it won't be in lecture, and
Okay.
it won't be in SI or my office hours, but I already sent out an announcement
Okay.
on Canva.
All right.
But I wanted to ask about like one 3 diaxles on that you have on the exam too.
Yeah.
So I think I just rounded my numbers because for this one, like the 1 3 diaxle between the ethyl
Yeah.
and the age, like I rounded it up to. So I got this, but you got this.
It's alright. It's probably just rounded.
Okay, and then
Yeah.
the same thing here. You got this. And then I
Yeah,
got
it's
that.
probably because we used like maybe a few like extra numbers in the actual energy.
Okay.
So I think it's just a rounding issue.
Okay.
You're fine, yeah.
And then did you give them the numbers, or are they supposed to?
They're not supposed to know numbers, but I provide a number. They should be like, oh, okay, it requires more energy to put this group in the axial position,
Okay.
and they should use that information to draw in the right
Yeah.
equatorial axial relationship. They don't need to calculate total energy or anything.
Okay, because
Yeah.
we had to do that. so-
Oh, you did? Okay. No.
Okay.
They have to do it on a homework, but I probably won't test that.
Okay.
Yeah. Okay.
I need to go grocery shopping. What am I?
I am not understanding how it was how you spell it. Enantiomers. I don't know how you write it. I couldn't see Yeah, he's telling me when he was learning this undergrad that he was fortunate enough to like get how to learn all of these studies and he still didn't understand it. Studying resources.
We don't have a lab that time, so we take it. That's just the week. It says the week. If you look at this, if you look at the next one, no. Did I say that? No, I have that. No, that's my no.
Thursday, are you gonna have us calculate the
Bond angle strength?
Yeah.
No. No, but you should know which one's like the most strained based on the shape we went over. Yeah.
No, I try to. I'm also lucky. Yeah.
Hope this works. All right, it's working for now. All right, so guys, let's come back together here. All right, so now we're going to talk about stuff I kind of went in passing as you guys doing the workshop last week. RNS, okay? Absolute. All right. So RNS, I like to think of it, you have a car, you have a steering wheel, and you either make a right-hand turn or a left-hand turn. So let's draw pictures of steering wheels, okay? So here's my steering wheel. I'm going to draw it another circle to illustrate the cushioning there. And at the center, you have a crossbar to indicate the steering, kind of the axles there with the wheel. All right. So if I think about making a right-hand turn, that direction, if we think of a clock, what do we think that illustrates? Clockwise or counterclockwise if we're making a right turn? Clockwise. So we're going clockwise in this direction, okay? Like this. So this is analogous to a turning right with a steering wheel, okay, with the steering wheel. Okay, and then if we go the opposite way, that'll be a left-hand turn, okay? So here, let's just write this to the far left so I have enough room. Okay, so the spokes of the wheel, I guess you can call this, the spokes like on a bike wheel. But on our steering wheel, we're turning left, right? So what direction does this look like? Clockwise or counterclockwise? Counterclockwise, right? You're going in the reverse direction. Yes, so turning left. Okay, so the way we assign R and S is that one of your atoms, so you have remember all our chiral centers, they're tetrahedral, 4 different substituents, okay? The lowest priority substituent should always be viewed going in the back away from you, okay? So I'll draw this carbon atom here. All right, so here is my first substituent. All right, so we assign priorities to the substituents, okay? So in this case, either 1 to 4, 1, 2, 3, 4, 1 is the highest, 4 is the lowest priority, or A, B, C, and D, where A is the highest priority and D is the lowest priority, okay? Well, for now, I'll show it in letters. So here's A. My B is going to look like it's coming in the back, going to the back, but it's actually situated to the side when we look at it from this side, okay? So that's B. And then here's in the plane of the paper. That's going to be C. And then going right here, you can't see it, so it's going to be kind of wedged that way towards the back. I'm just drawing it this way to illustrate, okay? And D here. So we're actually looking at this perspective. So here's my perspective. Here's the I. That's my perspective. So if I look at it this way, when you built the models, that D atom there, that bond is pointing towards the back. You can't see it, okay? So I wanted to make a note here that our lowest priority group In this case, groups are atoms or atoms or a bunch of atoms, like a functional group. Okay. Lowest priority group D is pointing at the back. Away from us. All right. Okay. So the D group has to be pointing away. Okay. So this is the same if we drew something like this. So same as. So here, this is the observer. All right. This is our observer. So RNS is a system to, denote enantiomers, and it was created in a special way, okay? And if we just kind of do our own way, it won't make sense because now it's not based on the system it was developed after. So it's going to be the same as this, okay? So my C group, we're going to situate it downwards here. All right, so that's a carbon atom, okay? So that's carbon. Our B group right here. And then here's my A group. And then right here, I'm going to say a D is kind of sticking outward, but we can't see it. So that's why it's towards the back here. And so we can't see that group because it's situated behind a carbon. But it's still there, okay? Now let's, so the priority goes like this. When you draw... when you go from A to B to C, what direction does it follow? Right-hand turn or a left-hand turn, okay? So let's connect the dots here. A to B, B to C, and then, C going all the way to A here. All right. What turn is that? Is that going to be clockwise, right-hand turn, or left turn, counterclockwise? Clockwise. So this is denoted the R configuration. So it's R because in Latin, rectus means right. Okay? So it has a specific name here. Rectus is not based on any English names. Okay? It has the rectus for right isomer, right-hand isomer. Okay? Now, if we think about the other isomer, okay, so here's something else that is true for enantiomers. Switch any two groups, okay, switch any two groups, you get the enantiomer. If you switch 3 groups or more, you get the same molecule. You get the same enantiomer, okay? So what I'm going to draw now, you're going to see 2 groups switched, okay? So let's go to now let's do the left-hand turn. So now we have a carbon atom right here. So I'm going to draw the dash line now. That's my A. I'm going to position that as my A group. Okay. This is still the C group. Okay. And then this position right here, this is going to be the B group. And then still going out towards the back here, that's going to be my D group. Okay, so I'm still looking at this position. So that's still my observer. So the observer is still looking at that carbon, okay? But now the positions here are going to be slightly switched. So A is where B used to be. So this is now A. Still C. And now this one's going to be B. All right, and D is still sticking out here towards the back. Okay. So remember, now we go from the A to B, right? A to B to C direction. All right. So is this a right-hand turn or a left-hand turn? Counterclockwise or clockwise? Counterclockwise. So this is the S configuration. Oh, sorry, I didn't mean to do that. So the Latin word for S is sinister. And that means left. So that's why it's R and S. Right and left. Okay? All right. So that's how you would denote the different enantiomers. If it goes from A, B to C, A is the highest priority. C is the third lowest priority. You're going to get an R enantiomer. If it goes counterclockwise, opposite direction, A, B to C, it's going to be S. Okay? Now let's talk about how do you determine the priorities here. All right? So there's some rules we'll go over, and we'll be able to get to some examples today. Okay? Hopefully. All right. So now let's talk about sequence rules. So this will make sense once we do some examples, real examples here. All right, so here assigning priorities to substituents. All right, so the rules here, they're named after three people: Kahn, Ingold, and Prelog. Rules. So Ingold is actually pretty famous. He had made many contributions to organic chemistry. Okay, some of the things I even still use in research. So, and it was true. But anyway, so number one. So you're going to assign priorities based on decreasing atomic number. So the highest priority, highest atomic number. Lowest priority, the lowest atomic number. Okay. So rule number one: assign. So in the lab manual, what we did last week, the rules are very detailed here. I'm basically going to summarize it, so it's very brief and succinct. Okay, so assign priorities to your substituents or to your groups of atoms here. In order of decreasing atomic number. So let's do an example. Okay, so it's not molecular weight. The only time you use molecular weight is when you have an isotope of the same element. Okay, so let's do this example. I think this is the one. I don't think this is the exact one I used in lab last week, but it's probably similar. All right. So let's use letters. Which one's the highest priority substituent? Iodine. Because I here, right, if you have a periodic table, that's why you get a periodic table. You'll be able to use this. I has the number 53, right? So that's higher than chlorine, fluorine, and bromine. So this will be letter A. What's next? Bromine. Letter B. What's the third? Chlorine. All right, and the lowest is fluorine in this case. In most compounds we see, it'll be hydrogen. Okay, but it's not always hydrogen. Okay. Now let's do a slightly different example where I drew a little curveball here. H, D, NH2, and then OH. All right, which one's the highest priority? So look at what atoms are directly bonded. So I see an O from OH, H, deuterium, D, and then N from NH2. So which one would have the highest atomic number? Close. Nope, not NH2. So which element comes the furthest down the periodic table? It's not D. D is an isotope of H, so that doesn't count. Nitrogen is not the highest, so what has a higher atomic number than nitrogen? Oxygen. So that's where A belongs. All right, what's next? Nitrogen, right? All right, then we have a tie. H and D have the same atomic number. Now you look at molecular weight. So what's the mass of deuterium? Well, we call deuterium heavy water. So it's heavier than H. If you have H2O, D2O is heavier. So deuterium here would be the tiebreaker because it's higher molecular weight. So that's going to be letter C. And hydrogen, usually always the lowest priority substituent. You can't have anything less than hydrogen, right? Good. All right, any questions about that one? So, little curveball there. Deuterium may look like hydrogen, but it's technically more massive. Yes.
Could you re-explain how you're because I don't understand how you're lettering stuff.
So A here is highest priority. So A, largest atomic number. D in this case is the lowest atomic number. All right, so which example? Okay, so does the first example make sense? Iodine, largest atomic number, furthest down the periodic table, and then fluorine, the lowest atomic number, highest on the periodic table based on these elements. And then for the next one, you look at the atom that's directly attached, all right? One has oxygen, one has nitrogen, one is H, and one is deuterium, which is the isotope of hydrogen, okay? So remember, nothing will be lower than hydrogen because it's the lightest element and it's the lowest atomic number first in the series, right? So that would be letter D, lowest priority, okay? And then A here, that's the highest priority. It has the highest atomic number, so that's why we gave it the letter A. So here I'll be say here, highest priority, lowest priority. Okay. Are any other questions on that one? It'll be confusing. So that's why last week in lab we didn't really go right into like doing RNS because there's a lot of rules we have to cover first. So last week's lab assignment, there's a lot of practice problems you can do for an RNS assignment, and I recommend doing that as part of self-study. Okay. If you don't want to do the problems in the book, the ones in the manual are perfectly good. All right. So that's rule number 1. Rule number 2. So you might be wondering, well, most of our carbons are going to be connected to other carbon atoms, so similar carbon atoms. So how do we break that tie, right? So this is where it gets tricky because you have to kind of play like a find the difference game, like finding Waldo, those type of games. You have to find the difference. Well, it's not as bad as that, but you have to find the difference in the chain to indicate, okay, this is where the chain's different. So this is a higher priority. This is a lower priority. You'll have to do that kind of systematically here, okay? So if there is a tie, so what do you guys think I mean by tie? Yeah, two carbon atoms directly attached to my chiral center, right? You'd be like, oh, they're both carbon atoms. What do I do now? Okay, so that's what I mean by tie. So, for example, two carbon atoms, for example, you're going to compare the atomic number of second. All right, so I say second, but what if there's a tie in the second atom? What do you do then? Go to the third atom, right? So kind of think of like second. I'm going to do second, third, fourth, etc. Okay, so the number of second, third, fourth. Okay. Atom in each group. All right, so you're going to continue doing this until the tie is broken, okay? So you will continue on until the tie is broken. All right, because remember nomenclature, we always said, okay, number to chain where the point of first difference, the numbering is lower, right? Remember we said that? Or, so here that's the same thing. You're going to compare the chains until the point of first difference is found where the tie is broken, okay? So let's do an example here. So we have a carbon atom, we have an H, now we have CH2, OH, CH3, and then okay, sorry guys, erase that. Bad. CH3, CH2. All right. So let's start with the easy one. Which one is the lowest? Hydrogen. So let's rank this one, letter D. Okay. Now, which one do you think is the highest priority? Well, all of them have carbon, and then most of them have hydrogens. Oh, wait, but the third one has CH3, and one of them has an oxygen directly attached. The other one has another carbon atom directly attached. So which one do you think would be priority number letter A? The OH, all right? Because both of them has carbon, right? All of them have carbon. They have some number of hydrogens, but one of them directly has attached to the C, an oxygen. And that's higher than carbon or hydrogen, right? So that's A. Now, how about B and C? Which one would be B and which one would be C? All right, the methyl, I heard C. Does everyone agree that methyl should be C? Right? Because what does the ethyl group have in addition to H's? Another carbon, and carbon beats out hydrogen. So that's why this one's B, this one's C. All right? Don't worry about assigning R and S here yet, okay? Does that make sense? So there's some problems on active where it asks you which one's the higher substituent, priority substituent. You're going to have an ethyl group, isopropyl group, and a terbutyl group. And so it's all going to be different based on how different they're bonded, okay? All right, but any questions about A, assignment of priorities? Remember, A is the highest priority, so that's like number one. And then D is the lowest priority. That's like the lowest importance. Okay. All right, so now we have to talk about double bonds and triple bonds. It's a little complicated in this priority kind of system we have here. So let's go to rule number 3. And that's it. There's only 3 rules. Okay. Multiple bonded atoms are equivalent to the same number of single bonded atoms. All right, so the things I draw here, they make no sense in reality, okay? So it's just for the purpose of assigning priorities based on this system of R and S, okay? So, for example, if I have this group, COH, okay? So we're looking at this portion of the molecule here, this portion on the right, okay? So this is the same as is equivalent brother to all right, so we're going to have this group here that's bonded to other parts of the molecule. So when I have a double bond, right, that's like I'm saying I have 2 single bonds between carbon and oxygen. So carbon has 2 bonds to the oxygen. Oxygen has 2 bonds to carbon. But when you look at a double bond, you might be like, oh, it's attached to oxygen, so this should have the same priority as an alcohol, right? That's not the case, okay? So what you have here is you have an H, and then you have 1 bond to oxygen, another bond to oxygen, and then the oxygens themselves are bonded to 2 carbon atoms. So this should have another carbon here, and this will have another carbon. Okay? So that's how you treat double bonds and triple bonds. So that's a double bond. Now let's talk about triple bond. Okay? All right. I know this is probably going to confuse people. Any questions? Does this not make sense? Any questions about that? No? Okay, so just think double bond, right? Just think of it as 2 bonds between those atoms. So carbon is bonded to 2 oxygen atoms, and oxygen as well is bonded to 2 carbon atoms. But as you look at the structure, it doesn't really make sense if you look at it from the actual group, the functional group, the aldehyde on the left. This is for the sake of priorities, okay? So if you had an aldehyde and then you had CH2OH, this one would actually break the tie because this one is only bonded to 1 hydrogen and also bonded to 2 oxygens. Whereas the alcohol we saw in the previous example, right, that's only bonded to 1 oxygen, that carbon. So this would break the tie, okay? But again, we need a lot of practice with this, okay? So that's why I'm telling you this chapter kind of most difficult in my opinion when I first took it, okay? And that's the reason is lots new topics we're talking about stereochemistry, okay?
Explain how you went from a double bond and then you have 2 oxygens.
Yeah, so double bond is like saying this carbon atom, right, is bonded 2 bonds to an oxygen. So in priorities, we have to break it up like this. Carbon, remember, on the left hand side, carbon is bonded, a double bond to oxygen. That's like 2 single bonds to the same oxygen atom, right? But we don't want to write it like that because in priorities, we're looking at the connectivity. A double bond is still connected to an oxygen, even if it's a double bond or a single bond, right? That carbon is still connected to the oxygen. We want to break that tie. An alcohol does not have the same priority. An OH doesn't have the same priority as a C double bonded O. So that's why we have to write it like this to break up that tie. Okay? So like I said, this is not what it really looks like in actuality. Okay? It's just for the sake of naming priorities here, or writing priorities for the substituents. Okay?
Are the carbons that are on the slide, do they represent two different carbons, or do they represent like the separate carbons?
Oh, this one? This group right here?
I can't see her.
This one?
No, on the right.
Oh, you're talking about these carbons, right?
Yeah.
No, they don't represent anything. So it's just for the purpose of priorities, right? Okay, because remember, in a double bond, what does that double bond mean for oxygen? Well, it means the oxygen atom is bonded to has two bonds to carbon, a carbon atom. But we can't write double and triple bonds for priorities because they would match the same thing as just having a single bond there. Okay? For example, you would say here, let's look at CH2OH. Right? Oh, look at this carbon. Both carbons are attached to an H, and they're both attached to an oxygen. So how would you tell which one has the higher priority? You can't, right? So that's why we write it this way. Okay, so both of these, they both still have this group, right? There's the same group here, CO bond. How can you tell which one has higher priority? Well, if this doesn't make sense, I'll tell you. If something has a double bond, that has higher priority than a single bond. Let's just put it that way. If the same type of atoms you're considering, C and O, double bond, triple bond, that's the priority order. Single has the lowest priority. Highest priority would be to the double and then to the triple bond. Okay, but this is how you kind of visualize this. So I'll put this in quotation marks because this is not actually what it looks like, but for priority's sake, that's how you should visualize it in terms of assigning R and S. Okay, Catherine.
So they do this because chiral centers have 4 groups, right? But
Yes.
Just, why would they even want to consider that like a chiral center? Because again, it's not the
Oh, this car. So these are actually. This is not actually a chiral center. This is just a substituent. So this would be. So this whole thing. These are substituents. Yeah. So this is a substituent. This right here. This is. This part is to the chiral carbon. Yeah. So the way we write this out is just to assign priorities. Okay. All right. Now triple bond is going to be even more nuts. So let's go over that one. So here's a triple bond. All right. CN is equivalent to. All right, so this is to the rest of the molecule, okay? So if I have a triple bond, that's like saying my carbon is bonded to 3 different nitrogen atoms. So, and here, and here, and here. And what does that mean for the nitrogen? The nitrogen is also bonded to what? Carbon, so 3 different carbon atoms. So you're going to draw something like this. C, 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 C. So it looks like that. So when you go to the point of first difference, you have to compare it like that. Okay? I know it doesn't make sense, but here in do some practice, okay? So the practice doesn't make sense. Say, oh, why is this a higher priority than this one? Come see me, okay? Or refer back to this picture. That's how we treat multiple bonds.
So this is just to help us like visualize. Are we gonna have to,
Yeah, finding the point of first difference, like in question number 2.
are we gonna have to know this, like put this on an exam?
No. So you just have to assign A, B, C, or D. But when you look at multiple bonds, this is something you might have to consider how you should visualize it in order to assign the priority. You don't have to rewrite this, no. Just checking, good. Okay, any questions about assigned priorities? I think the best thing to do now is just, go over some examples, okay? So let's go over an example. And so the reason why this homework chapter 5 is so long is because there's a lot of topics like this, and I want to make sure we understand all of it, okay? So let's draw S cyclohexane. So not cyclohexane, S methyl. This should be 3-methyl. All right, so now there's a new way to draw nomenclature. Write nomenclature now and draw it. Oops, my bad. You're not supposed to see that. He passed away this April. Yeah, it was really sad. He cost a lot. I would say probably over $8,000 in hospital bills. Yeah. So we loved them. So we forked out the money. It was really sad. Like 3.5, 4. We got him during the pandemic, like in 2022 or 21, I think. Yeah. All right. Well, I lost my place there. We have another one though. We still have 2. It's kind of sad because my brother's bunny, who he had for like 5.5 years since a baby, he passed away too. Like hours within each other on the same day. It's very tragic. It's a very sad day. But we got some new ones, so I guess that's how we cope with the loss. All right, 3-methylhexane. Okay, so there comes a time where the molecule is not drawn in the right orientation, and that's why we built the models in lab. We have to rotate it. Okay, so I'll draw this molecule in one orientation. All right. So we have CH. All right. So I'm just going to abbreviate this so it's easier to look at the chiral center. So C2H5. Okay. And then coming off the wedge group is going to be my CH3. And on the dash bond is going to be the other part of the carbon chain, H7C3. So that's the propyl group. So on the chiral center, there's a propyl group, an ethyl group, methyl group, and a hydrogen. All right. So let's label the priorities here. All right, which one gets A? Not the C2H5. C3H7, yeah. All right, because C3H7, right, you have CH3, CH2, CH2. For ethyl, you have CH3 and CH2. All right, so both of them will have CH2, right? So what's the difference here? CH3, CH2, but also the C there. So this one would win. So longer alkyl chains will beat out smaller alkyl chains. And then more branched alkyl chains will beat out linear chains because of the substitution pattern. Okay? So there, that will be A. Then what's B and C? B is C2 and C? CH3. All right. So you might think, well, if we do the priorities, what is the stereocenter going to be? R or S? What does it look like now? Is it clockwise or counterclockwise? Clockwise, but is clockwise S? No. So the reason is hydrogen is not in the back. Hydrogen should be where A is, right? That's where the back is. So we have to rotate this molecule where the H is going to be in the back, Okay, so this looks R. Looks like R. Okay, but the hydrogen is not in the back. But H is not towards the back. All right, so we're going to have to rotate this molecule on as drawn, okay? So what I like to do is you're going to rotate here. And here I'm just going to rotate, like we did in the lab, rotate 120 degrees because it's tetrahedral. All right, but where you're going to rotate, I'm going to draw this line here to indicate. All right, maybe don't draw like that, but all right. So I'm going to rotate around this axis of rotation. So my CH3 group is my pivot point. I'm going to rotate around there, okay? So when you rotate this, the axis you drew the line to, that stays fixed, okay? So here, we would draw our carbon atom. So I'm going to rotate it sequentially here so you can see the transformations. So CH3. All right, so I'm going to rotate this. Let's see here. Let's rotate this clockwise. All right. So here, the H has now replaced where the C2H5 is, and the C3H7 has moved to the top. All right. Okay, are we done, though? Is the H in the back now? No. So I had to do it one more time, okay? So if you can do this right away, if you can just say, okay, I'm going to rotate it like, say, 240 degrees, and now the H is in the back, go ahead and do that. But if you can't do that right away, just practice rotating this and saying, okay, I'm rotating around the CH3 group. Let's see how those positions change, okay? And if you do this with a model, it'll look exactly as we have drawn it. So we're going to do it again. Rotate again in the clockwise direction. So rotate again. All right, now C here, we still have the methyl group in the same position, okay? And then C3H7 would appear over here. C2H5 has moved to the top position. Now H is in the back. Now it's not an R and S. What is it actually? S. So letter D, A, B, and C. So we're going in this direction, right? Is that clockwise or counterclockwise? Counterclockwise. So this is S. Okay? So another way we could do this is if we look at it from a different perspective. It's not in the plane. Now we're looking at it from a 3D perspective, okay? So this is the same as if we drew it like this. So imagine you look at it from this perspective. So if you look at it from this perspective, okay, like that. The CH3 and the C3H7, they will come out at you, all right? And everything behind it will go in the back. So that's why I represent right here, okay? If you look on it through the bond angle, two of them will come at you. The bonds in the back will go in the back. So you visualize the H that way and assign priorities, you'll get the same answer, okay? So A, B, C, D. And this way is still counterclockwise, so that's S. Okay, so that's another way you could look at it. All right. So it might have been possible if we did it that way. If we had looked from the first structure, the alternate direction, if we had looked at it from this direction and drew this structure right there, this structure right here, we might have not had to rotate it, okay? But that's hard, so I wouldn't recommend doing that. I would just rotate it, okay? Because the other thing you could do is, say it's R, right? But the hydrogen is not in the back. You can be like, okay, well, the hydrogen's not in the back, so it should be the opposite of what I look at. So you can say, oh, it's written as R, it should be S. That's another trick you can do. This one's not a great example. Another trick you can do is something called the right-hand rule. I might show that next class, okay? All right, so let's see. So I want to kind of talk about what this structure is, and then we'll end for today, okay? So this is actually a specific structure. This is called a Fischer projection. All right, so in biology and chemistry, we typically draw sugars in a very cartoonish way, even more cartoonish than bond line, and that's because there's many carbon atoms with the same kind of groups on it, all right? So this cross projection here, that's called, remember we had Newman projections? These are called Fischer projections. So let's just talk about them really quick. Just introduce it, of course. All right, so the Fischer projections, they show 3D arrangement on a page for a compound. All right. So a Fischer projection looks like this. It's a bunch of crossed lines, and each cross here, so each of these points here are carbon atoms in the tetrahedral carbon atoms, okay? All right. So in the Fischer projection, the vertical lines here, so these vertical lines here, these are bonds are away from you, are away from the viewer. All right? And then the horizontal bonds, this kind of looks like what I drawn here. The vertical bonds situated away. The horizontal bonds now, they are towards the viewer. So these bonds right here, those two bonds here. Bonds are towards viewer. Okay? So, what we usually write this as, say you have a carbon atom, right? W, X, Y, and then Z. All right, it's like you're taking your molecule here and you're pressing it flat. So we're going to press this flat. And what we get is a crisscross shape, Z, Y, X, and W. Okay? So to wrap this up, let's just compare the dash wedge drawing to the Fischer projection. So for a carbon atom, say you have 4 groups around it. Looking at that orientation we draw on the page before, OH, H. So this would be my dash wedge structure. So dashed. So you can have 2 wedge bonds as long as, you're looking at this orientation. So this would be the dash wedge structure. And then here, we convert it here. They're all horizontal lines now. You don't even show the carbon atom. OH, CHO, and then CH2, OH. This is my Fischer projection. So the important part here is that we have to use these Fischer projections and basically assign stereochemistry. All right, so it's part of R and S. And we'll go over how to manipulate Fisher projections and assign R and S to them on Thursday. Okay? All right. Good job.